Hi, I'm Prav. You have to say. I'm Tom, and we need to stay tough to solve fusion.
Awesome. Okay.
Welcome to Tough Tech Today with Mayan and Miller. This is the premier show featuring trailblazers who are building technologies today to solve tomorrow's toughest challenges.
Let's go. Welcome to Tough Tech Today. Today is the third part in our series on fusion. And today we're honored to have with us two guests from Focused Energy. We have Prav Patel and Thomas Forner. Focused Energy is enabling secure energy harvesting from direct laser-driven fusion and developing a completely novel range of non-destructive testing for industry based on the same technology. Their technology is also very modular, which enables its use throughout industry. So we have Thomas Forner here. He's the CEO and founder of Focused Energy. Prior to Focused Energy, Thomas was a serial entrepreneur who loved working with data and people. He has run various ventures in the fields of e-commerce, nutrition, and software, building and scaling companies of various sizes. We also have Prav Patel. He's the Chief Technology Officer of Focused Energy. Previously, he spent 20 years at Lawrence Livermore National Laboratory on inertial fusion and is one of the program leads at the ignition experiment at the National Ignition Facility that generated net positive fusion. Thomas, Prav, thank you very much for joining Jay Mill and I today on Tough Tech Today.
Thanks for having us. Thank you.
So let's kick it off with really quickly, like, how would you summarize? We've talked with a bunch of fusion companies so far, and how would you summarize kind of your approach to fusion, and based on all the other companies out there, and kind of what makes your company unique and special?
Focused Energy is special because we really look for commercializing fusion as early as possible. As we see, one of the biggest challenges in fusion is to raise enough capital and also not to build another national lab, but to build a company and focus on customers and products. That's why we have developed a modular approach to fusion that allows us to untap markets early on to generate revenues already this year. And ramping up revenues to 100 million by the end of the end of the 20s, and then really paving our way to fusion and unveil fusion ultimately in the 30s.
Amazing. Yeah, that is definitely a contrast to what we've seen on some of the other companies where we've talked to, as they're very, very focused on the end goal, but they do acknowledge that it takes a huge amount of capital to get there. And if you're not gonna, have this unlimited source of capital, like how do you sustain yourself if that's your business plan? So that's very unique. What's been the hardest part about, or has there been a big challenge in kind of finding the alignment between near-term markets and kind of your long-term goal, and making sure that you're still pointing in the right direction of the ultimate goal while you serve the near-term customers?
Of course, it's. I guess this was the biggest challenge, but also our concept from the very beginning. So we see fusion companies as let's call them wave makers, not wave riders. And so what we need to do is we need to build a whole new ecosystem. And this cannot only be done by just one company. And you also need strong partners, industry partners. And these industry partners typically are risk averse. So you need something that attracts them to invest into these markets. And this is technology that we are developing and that we productize and market early on. So first step is that we have started with a completely outfitted and operating target lab. So we build our proprietary targets, but at the same time we produce targets for other labs. That's a small revenue stream, but a growing revenue stream. Second step is that we use the lasers that we build, that we develop, the targets that we develop, and diagnostics that we develop anyhow for fusion, and just assemble it differently. So like with the Lego bricks, and built a non-destructive testing machine early on, a neutron source, a muon source, an X-ray source, with a micro accelerator business. And this is going to be the product that we are launching in 2.5 years from now. We already have a first customer, pilot customer, a German energy company. And we do non-destructive testing for nuclear waste. So we analyze nuclear waste barrels. So we can look through them with with our machine and can detect what is in the inside. And this is just a huge change for this market, because today the only way to analyze it is open the barrels, take a sample, close them again. This is expensive, this is time consuming, this is dangerous. And we found a completely new way to do this. Also, this is the way how we develop the laser for fusion and ultimately build our fusion power plant with a combination of lasers, targets, and diagnostics as well.
That's really interesting. Is this an approach that is has less direct heritage to the famed WX7 facility in a reactor than some of the other sort of approaches to fusion that would be maybe like sort of direct lineage to team members or to the discoveries of that reactor?
The WX7, you mean the stellarator?
Is correct. Yeah. Is there any sort of relationship other than the fact that they are also working broadly in the fusion realm?
Oh yeah, our kind of heritage goes back to NIF. So
so completely separate.
Yes.
Yeah.
Yeah. So WX7 is a magnetic fusion device, and we're studying our approach is inertial fusion energy.
Okay. Does that make it so that in terms of I'd like to understand the access to talent for fusion systems then. So it's not necessarily that someone who may have had as much experience on a stellarator design, it's not like they can just move organizations over to focused energy and plug right in. There's actually a lot of sort of separate sort of physics at play then for the approach that you're pursuing versus some of the other kind of companies that we have looked at in the past.
Yeah, so there's two kind of big approaches to fusion. There's the magnetic fusion and there's inertial fusion. So magnetic fusion has been principally funded through government labs pursuing fusion energy, and nationally and then internationally with projects like ITER. And they're pursuing tokamaks and stellarators and devices like that. Inertial fusion comes from a history of work on high energy density physics, and basically ever since the laser was invented back in the 1960s, physicists realized that they could use lasers to create very high energy density matter. And back in 1972, there's this very famous guy, John Knuckles, from Lawrence Livermore National Lab, who published this concept for the first time of using these high energy lasers to implode small pellets of deuterium and tritium, and calculated that if you did this implosion just right, you could compress deuterium and tritium to densities and temperatures higher than the center of the sun, and you could initiate a fusion reaction, and that fusion reaction could potentially produce hundreds of times more energy out than you put in. So that concept was first published in 1972, and national labs, particularly national security labs in the US, in all over the world, in France, in the UK, in China and Japan, have been pursuing this concept of laser-based inertial fusion. And it's taken 50 years to do, but the National Ignition Facility was kind of like the final machine in a series of increasingly larger laser machines that were built specifically to try and achieve this, and to try and achieve ignition. That is producing a thermonuclear explosion that produces more energy than you put into it in a laboratory. And that's what the National Ignition Facility at Livermore was built for, and what it finally achieved, in this last year. And then there's other labs around the world that have been pursuing that concept as well. So our scheme kind of directly comes from there. So in terms of like our team members and our talent, we're drawing from that community. And we can also take advantage of laser technology developments over the decades that have been invested in, like by the US government and other governments, target technology, simulation, code capabilities, diagnostics, etc. So we're kind of really starting from a very mature, scientific and technological kind of stepping stone, and kind of launching from there.
Yeah. So that when you talk about that moment of ignition achieved, what really did that mean for the industry, and especially on the commercial side? Like, how did it change the landscape and perhaps enable your startup to flourish?
I would say it has not immediately changed it. It's still about to change it. It took some time. That there's a lot of education that is needed for the investor space, and that's what they all have been doing for the last 24 months, to hire experts to get a deeper insight into the different fusion approaches, and finally they have seen the net energy gain from NIF. This definitely has changed the view on inertial fusion. So this is now seen as one of the main approaches to fusion, and maybe one of the very interesting ones when it comes to commercial viability in the long run. As you build on lasers, as you build on industry lasers, as you have a proven technology also that has changed other industries, like chip production recently, like automotive manufacturing, where you use lasers at a high rep rate, 24/7, running for 7 years without maintenance. That's what we want to build for fusion. And this is ultimately then a cheap source, and it's about the cost for the levelized cost of electricity. So will we have a competitive price for electricity in the end? And that's how we build focused energy.
With the idea of building something that's able to run for such a long duration, is somewhere in there where the modular concept comes in terms of like how to size for a future projected grid base load, and how then do you build a system that is kind of more like an elastic in that sense?
Yeah, I mean, it's determined by the size of the target and the amount of laser energy you need for igniting it and for getting a net energy out. So there's a sweet spot that we are aiming at. It's probably at the lower end at 0.5 gigawatt electricity to the grid, and on the upper end probably 2 gigawatt or maybe even more. And this is determined by physics in between. So how much fuel can you assemble? How many lasers do you need? And the modular concept means we are conceptualizing the lasers, so rather small lasers, and many of them, so like a couple of hundred or maybe 500, 600, 700 lasers. And you just add more lasers or less lasers depending on how much energy you need on the target.
Hey, you mentioned there's a lot of education needed in kind of the investment market. What do you think the biggest misconception about fusion is from the venture capital community?
Yeah, I mean, it's one very important aspect is timing. I mean, we are all building complex machines. We are all building in concrete. So this means you have long time frames for building that. This is typically not in the range of a typical investment for a VC investor. So this means they need to you need to find concepts how they can invest and then exit someone, because typically they have time frames of maybe 10 years or 10 years plus 1 or 2 if you are the very first investment in a fund. So that's one hurdle. The other hurdle is if it's a binary bet. So if it's really, you don't know today whether you're going to make it in 15 years or not. So it's a really binary bet. And I mean, of course, we are addressing the by far biggest markets than you can address. But I wouldn't do binary bets. So this is one more additional thing. The other thing is the community is very, very small, both in magnet as well as in inertial fusion. So you only have, let's say, a couple of hundred people globally who know about fusion, and there are many approaches that are, from our point of view, not scientifically anchored. And we believe in science. We believe that approaches need to be scientifically anchored, and we also believe in publishing it. That's one challenge that investors need to overcome, to differentiate in between approaches that might look nice at the first view, but turn out to be just impossible. And that's what we see quite a lot.
Do you feel I would think we would all agree that like a tough tech company would be at the core is science advantaged and thus scientifically anchored. Of some of those other approaches that they feel may be sort of less backed by science, is it perhaps an issue with, I mean, probably the teams around it may not realize that, right? That they may have their blinders on, so to say, or not realize that some aspect of the science and math and engineering actually is a big unknown, and that they're going ahead anyway at the risk of it not being sort of invented in time. They're kind of driving along the road and it's not paved, right, too far ahead of them. And so is that something that there would be perhaps some sort of rough, maybe painful sort of contractions of some of the fusion companies, the for-profit ones at least, right, that may not realize till it's hundreds of millions of dollars after that they actually didn't have sort of the science figured out in time.
Yeah.
Okay.
Yeah.
Okay. Yeah, that's a tough thing for the industry, and something that we kind of see playing out maybe a couple years ahead of time with like autonomous cars. You and I were talking ahead of recording that is, with the autonomous car industry, there was a lot of I think appeal and thought that it could be sooner than later. Fusion in some parts, some folks I think would say it may also have that kind of feeling that maybe it's feels like it could, like a quantum computer, 5 years, perpetually like 5 years away. However, with autonomous cars, that's analogous to something that like we experience almost every day driving a car around. Whereas with a big project, like an infrastructure level project, is something that maybe those investors and the teams building it, like you, are aware of, that these are measured in half decades or multi-decade endeavors, right? Compared to the autonomous car folks, which maybe had a shorter time frame in mind.
Okay. We'll get there, autonomous cars soon.
Well, yeah.
But it's going to take time.
Full self-driving beta is still very much more like alpha, but
I was in San Francisco 2 weeks ago, and it's amazing seeing all these robot taxis driving around.
yeah, but I think maybe just after you left, perhaps. I mean, Cruise was sort of, I think, forbidden through regulation from driving because of very recent pedestrian injuries and deaths.
That's exactly happened when I was there.
Yeah, and so that was like a flash in the pan on the scheme of autonomous car technology, that cruise vehicles are around, no driver, just paying passengers on board, and now they're kind of tucked away back into corners again on private lots because people are getting hurt. But fusion, I would imagine, would have, it's a completely different kind of risk calculus, so to say. One, it's not fission, which we are aware of, kind of, things go wrong, it kind of go boom. It sounds like that with fusion, if things go wrong, the whole thing just kind of shuts off.
Yeah, it's just nothing happens. You just don't hit the target. There's no implosion. There's no energy. There's just nothing.
So there's no like death ray laser beam. I'm picturing kind of like the Death Star going wild.
Yeah, what if you point it the wrong way?
Right.
But I think there's still like a educational hurdle. That's one of the things where we, along with the other fusion companies and the whole fusion community, is trying to do, I think, is educate public and people on the differences between fission and fusion, and that they're really like worlds apart in terms of like safety and hazards.
Well, the private sector is something that, let me say it differently. We have safety, certainly. I mean, and educating the market is very important, of course. But then there was a decision that each of you must have made, and to say, this is time to make a for-profit company as opposed to a nonprofit or maintaining in a government or research lab somewhere, saying, it's time to kind of quote unquote sort of spin out. And that could be an incredible way to access the power of the private markets to manifest something that actually will make an impact, right? So it's not just sitting in a lab. But could you walk us through the mindset that you've had and maybe some of those decision points? Because I think there's a lot of entrepreneurs. Some are a little bit too quick to spin out. Others, researchers that may be like, well, let's just stay in the lab and just keep working on like whiteboard equations. How'd you decide?
And for me, as I said, this has been like a 50-year kind of endeavor to achieve ignition by like inertial fusion, to achieve a burning plasma and a plasma that can produce more energy than you put into it, like for the first time on Earth. So there's been, especially in the US, there's been a huge amount of government investment in national labs and in these kind of facilities, like I was saying, in the codes, in the underlying science, in the underlying technology, particularly for laser-based inertial fusion, which is what we're pursuing. So for me, I think when we actually kind of hit that milestone of ignition 2 years ago, then all the attention was, okay, not okay, we've done it once. Now you need to do it repeatedly. And now the discussion was all about fusion energy and how to produce fusion energy, to address climate change so for me, then I was looking at how you do that within the national lab, within the government kind of, infrastructure. And it takes a long time. You're writing proposals, you're developing the community, you're trying to get government funding, because this is all government funded, and these things, it takes a long time to do that in government. Then with private industry, I could see that you could the benefits of trying to pursue a commercialization strategy in the private industry side. You can spend money fast, you can make decisions fast, you can tolerate much more risk in the private sector than you can in the public sector. So you can move. So I kind of became convinced that you could actually move several times faster, and you could do what might take 30 or 40 years in the public sector. You could do it in 10 or 12 years in the private sector.
So kind of to follow on that, like on on your own journey. Can we rewind a little bit, maybe even a few weeks before that ignition experience happened to the founding of Focused Energy? Thomas, can you tell me, like, what were you thinking when you decided to found a fusion company? You know, you have a very diverse background and a lot of different industry, and you woke up one day and you said, "Today's the day. We're gonna solve the world's energy crisis."
Yeah, kind of, no, but not really. So I was working for with other investors and startups on deep tech, different technologies. So, and then coincidentally came to fusion, and I got to know Marcus, so my co-founder, Marcus Roth, and he is one of the most amazing guys I've ever met. He and it's like it was feeling like something really big, probably something, if you look back in 50 years, it's the point in time in humankind when there was probably the biggest change that ever occurred. So we have the chance the first time unveil the holy grail of energy and really increase the availability of energy by 1,000,000 times over. And this is going to change anything that we are doing today. And being part of this is the best thing I can imagine. And having a broad overview of different technologies and how they come together means laser development on the one hand, data, quantum computing, AI on the other hand, material science, nanotechnologies, the third pillar. So this is seemed to be for the first time that different technologies are mature enough to make it happen. And now it's the only thing that we need is to start integrating it. And then we were betting on NIF. So Marcus was also working at NIF 20 years ago. And our bet was that NIF would show ignition and net energy gain. And we thought our goal must be to hire the best people in this space from the renowned labs, and that's exactly what we did. And then it was coincidence that NIF was demonstrating the first ignition shot, and then a year after, a bit more than a year after, the first net energy gain. This was really coincidence, but this was our bet from the very beginning. And it's could not have been more exciting as it was to have such fantastic people around us, and wherever it leads us, we are going to contribute that we unveil fusion.
That's really incredible. The two locations, two different countries, two different continents I'd like you to walk us through the strategy of that. And I suspect it has to do with those kind of like the legs of the stool that you had mentioned before in terms of sort of relevant technical domains. So what is it? US, Germany? Why and how do you do that?
So we started with University of Darmstadt. So we took over IP and the target lab of University of Darmstadt. This is where Marcus has his professorship. And then we knew that we need to work with the US labs, as they are the most advanced in science, and we wanted to build on their breakthroughs. And that's when we reached out to Livermore. That's when we reached out to Prav. We got Prav on board very early. We got Bill Goldstein, the former director of Lawrence Livermore, at the very beginning on our board. We have Debbie Callahan also in our team full time. She was designing the targets. She was also in the program lead with Prav together. So we have 2 of 4 scientific leaders of Livermore on our team. And it's really a combination of strengths in the US, mainly the science, and also the regulation, which was much more advanced at this time in the US, and German engineering, where you have fantastic laser companies, where you have the leading laser companies in solid state lasers. So like Trump Laser Systems is one of them. You have Fraunhofer, where laser development is taking place, and bringing these advantages or these opportunities together was our idea. And also we thought energy has always been is global. I mean, we have of course geopolitics today, but still it's a global good, and we need regulation in all major countries. So we need to solve it in Europe, we need to solve it in the UK, we need to solve it in the US. That's what we are supporting as well. And we knew, or we were also betting that governments will start investing. And it then turned out that the DOE is setting up a program, now Germany is setting up a program, UK already has a program. And we created a structure that allows us to apply with different parts of what we're doing in different countries or even on different continents. And that's what we have been doing. And we have succeeded in that. So we have raised public funding from US, from Germany, and from the European Union so far.
Awesome. Yeah, that's a very good strategy. So you can build on grant money and you're not diluting yourself out. And
yeah, and you know, you need to, because the amount of money that is going to be needed for fusion is huge. And as I said, we are pre-product, we are pre-revenue. We don't. I mean, we are trying to make a difference in commercialization, but still, it's a challenge. It's a challenge to build the first product, and it's always hardware. And for building hardware, you always need a lot of money early on.
Yeah. How do you keep your teams connected as they work on different parts of the world?
Yeah, it turned out to be one of the major challenges for a while. So meanwhile, I would say we found each other. So we are kind of working virtually from the very beginning on. So we do teams. We have created structures that allow us to do project management. I mean, actually, we use the same as in software development. So we use Jira, Confluence for engineering projects, of course, MS Project for if we do a design freeze and then detail it out. There are different methods still. But to keep the overview, the software industry has told us how we can work agile and keep people from different cities, different continents together. And the time zones even help because we never stop working. When we stop in Germany, we start in the US. So
it's like shift work.
yeah. That's incredible. I find it really inspiring for I mean, some of the toughest of tech that is like where there are some aspects that are able to be done in silicon and like, you know, simulating a digital twin or whatever, the equivalent for fusion energy development. But there are very sophisticated site specific kind of work that also needs to occur, and that you are finding that kind of maybe that new normal of a hybrid a way of doing that. It's something that maybe for with your company too has been growing in terms of multiple sites, multiple clients.
Yeah, we've definitely employed a similar strategy, the lunar rover business. So we have an office in Luxembourg focusing on a particular technology that's interested to the Luxembourg Space Agency and European Space Agency, and we have an office in Australia also kind of for some technologies that they're interested in. So, but it really helps, I think, you know, it kind of helps the nations and the country and the company itself work together, but helps the nations kind of feel like they're kind of all collaborating towards a goal that really, you know, in fusion and kind of in my passion space, I think really should be a global goal of, you know, solving some of these challenges that face humanity. Energy is probably more important than space exploration, but they're tied.
And as you've just seen, the US Department of Energy and the UK Department of Energy have started a collaboration.
Exactly. Yeah, that's great.
Yeah.
And the science is all the same, right?
It's all science. So speaking of collaboration, I would like to learn a little bit more about how you collaborate with other companies in the industry, because like you said, you know everyone and you found ways to kind of like provide targets for some companies And how do you balance, cooperation and competition to something that works for everyone involved?
I would say it's easy. The more different the approach is. So collaborating with tokamaks and stellarators is easy, but also the overlay is not that big. So we have maybe kind of similar challenges when it comes to reactor design, first wall, tritium breeding, the fuel cycle. So this is where we definitely where collaboration is very easy. It's more difficult in the IFE space, but maybe Prav, you had recently some contacts, but there are some interesting approaches maybe.
Yeah, I think we're at such an early stage, and there's been this huge growth of new fusion companies in the last few years. Still, most of them have been in the kind of magnetic-based systems. In the inertial fusion space, it's still really just a handful of companies around the world. So I think right now we see far more benefits from sharing and working together and trying to promote inertial fusion as a really viable route to commercial energy than we do by competing.
What you mentioned earlier in the need to educate the market, and also that there's becoming a more abundant government origin, like non-dilutive sources of capital or grants. Have you found as a company that you've needed to develop, say, regulatory strategy, maybe even like hiring of lobbyists to go to sort of respective like nation state capitals to talk with either Congress people or whoever, regulators broadly, and also to be able to kind of get sort of written into upcoming requests for proposals? Could you because I know that regulatory aspect is something that a lot of startups face, and it's kind of like a black box for a lot of us.
Oh, that's what we've been doing from the very beginning on. So both in US and in Germany and Europe. So we are very well connected to politics. We have someone sitting in Washington here in the US, permanently taking part in all the meetings. And of course that's where we collaborate, by the way, also with other startups to work together on regulation, to work together on the fundings that are available or that maybe become available, and same in Germany. So you need to have a close contact to politics, and in the US to the Democrats as well as to the Republicans, because in the next election we definitely want everyone to pursue fusion investments. Same in Germany on the different levels, with the different parties, and Europe is the most complicated thing. Yeah? So the European Union, where you have then too many people at the table.
Yeah, it does take a lot of signatures to get something done, but we've seen with like the NATO Innovation Fund, that's raising a billion euros. That was what I think they got 27 signatures, and so that's stuff happens. There's a lot of sort of capital. It's just kind of a lot of colors of money tucked here and there, and then in Germany, sort of a different driver. It's fascinating.
Okay.
So would you go as far as saying that your regulatory strategy is kind of a competitive advantage for Focus Energy in contrast to plenty of other companies?
No, I don't think so. I mean, it's a competitive advantage being connected to politicians and being known as. So we definitely want to be the leader in inertial fusion energy, and we want to be seen as that, and that is paving the way to get additional funding. That's definitely going to be a competitive advantage. And that's why you then can profit from programs that come up as soon as they come up. But in terms of regulation, it's more for the market as a whole. and it's pretty much we've seen it in the UK. They have demonstrated how this might work out. So they have put fusion into environment and medical. So it's now treated as a proton therapy center, and not as nuclear anymore. And that's what we aim for.
So, are you ready for this question? You got an awesome whiteboard behind you. May I ask what's on it, or is it the secrets to fusion energy?
It's our secret formula. So
I was debating whether to wipe the whiteboard just before.
You see, we did not.
Here's someone's mechanical engineering homework.
Yeah. Yeah.
Like we got some stress and strain going on.
No, it's just our like strategies for like our approach to
Take over the world.
Basically like our science and technology research paths to kind of de-risk science and technology. One of the advantages of inertial fusion is because it's very modular. The lasers are separate from the targets, are separate from the reactor chamber. You can work in parallel on these things and kind of bring them all together into a single integrated system. But you can develop the technologies independently before bringing them together.
And the milestones help us to measure technology readiness levels. And what we want to do is we want to increase the TRLs and ultimately then build what you call in other branches a minimum viable product that allows us to demonstrate all the technologies that we ultimately need for a prototype fusion power plant, but for much less cost. And that's what we aim for.
What's your number one technology priority? Like, what's the thing that needs the most attention to increase the TRL?
It's hard to choose between. Inertial fusion, like, is the two key ingredients are lasers and targets. And so we're kind of working hard on both of them in parallel. They're both big challenges. Like, for each of them, we know how to build one, once in kind of low quantities. So for lasers, we can build a laser to the right specifications that you need to achieve inertial fusion. Livermore's demonstrated that. But then to make it to what you need for commercial energy is a laser system that's much more energy efficient, that's much lower cost, that's much more reliable, that will shoot 1 million times a day very robustly and reliably. So that's the technology challenge there. And then similar for targets. We know how to produce these targets one at a time. And again, we have to produce those 1 million at a time, 1 million a day. Again, high production volume, low cost. So both of those are, a big technology challenges that are kind of independent and that we can work on in parallel.
Can you paint a mental image for me of like what one of these targets looks like? Like, I'm really curious on the size of it. Is there geometry that matters, or is it just kind of a material composition?
Yeah, and this is one of in magnetic fusion and inertial fusion are very different in lots of different scales. So in magnetic fusion, you have a big machine that you fill with DT gas over a very large volume, maybe like several cubic meters of volume of gas that you try and heat up and achieve fusion. In inertial fusion, these pellets are perhaps
size of a peppercorn.
Yeah, a few millimeters diameter capsules of DT that contain just a few milligrams, very small quantities of DT, and that's what was shot on NIF. A tiny little pellet around 2 millimeters in diameter, filled with some DT gas, and On NIF, that was placed in the center of the chamber, very carefully inside the center of like a 10-meter diameter vacuum vessel. And 200 laser beams came in and fired on it. They used this scheme called indirect drive, where they hit the capsules inside a can. They hit the can, it produces X-rays. The X-rays hit the capsule, heat up the outer surface, ablates, and you have this rocket reaction that then compresses the inside of that tiny little pellet of gas. And if you get that to the, pressure and temperature higher than the center of the sun, it will start fusing. And if you can get it to high enough pressure and temperature, it will fuse, produce energy. That energy will self-heat that implosion to where you no longer have to provide energy. That DT will just heat by itself, increase in temperature, and produce very large neutron yield. And that's what happened on NIF with one pellet. And so now to go to commercial fusion, our targets kind of look the same, but now you have to inject them. You have to inject them at something maybe like 10 times a second and fire the lasers 10 times a second. And if you can do that with these tiny little quantities of DT, you can get to like gigawatt electric power levels.
So if you want, we build the nuclear combustion engine.
Basically, yeah. Huh.
But that's one of the kind of inherently safe features of this is you're using tiny amounts of fuel, a shot at a time repetitively.
You had mentioned earlier about how you're able to take, I think it was nuclear waste, and be able to do like an inspection on that. I don't understand how that kind of inspection is related to the other aspects of this fusion.
It's mainly depending on our approach. So our approach is a bit different from what NIF is doing. So we compress the pellet directly with lasers, and we then have divided this whole process into two steps. The first step is compressing with lasers and creating this dense plasma. And the second step is igniting it with a spark plug. That's why I call it the combustion engine.
Oh, okay.
And the spark plug is a micro accelerator. So we shoot with a different pair of lasers into a cone that is sticking in the target, and we shoot on a foil that is in the cone and accelerate the protons from the backside of the foil and create a proton beam, and the proton beam then hits the dense fuel and ignites it. The reason why you don't use lasers directly, because the lasers don't get in anymore because it's too dense. So you need ions to get in, and the best ions to do this are protons. And this is a micro accelerator that we built, and the same concept can be used for accelerating other particles. So we can accelerate neutrons, we can create X-rays, we can create muons with the same concept, and that's why what we call the modular concept. This allows us to use to build this accelerator early on and build a different product out of it.
Well, I think something that as we come toward the end of the episode, I'd like to offer, are there certain kinds of what you're looking for as a company? Are there certain kinds of people, whether it's by demographic, specialty, et cetera, that would be helpful? Or any other sort of points that you'd like to make advocating for fusion and Focus Energy's approach to it? This is your time.
Sure. I mean, talent is crucial. Scientists as well as engineers. And we just need really people that bring along experience, or at least excitement, and ideally from also not from it's always difficult to bring in someone who has too long worked in a corporate environment. It always takes a while to adapt to a startup because it's a very different way of working. And therefore, ideally, deep tech startups, engineers from deep tech startups who want to join a fusion company. That's exactly what we're looking for.
Closing words for us?
No, I just really want to extend my thanks and appreciation for having both of you on our show today. I think all of our listeners have been really excited to see another perspective from fusion, especially for a completely different approach than that they've learned about so far. So thanks again for joining us, and best of wishes on your endeavor. We definitely need the energy, so go make it happen.
Thank you.
Thank you.
Thanks so much. It was great talking to you.
Thank you.
Yeah, thank you so much.